Okay, just a second.
Ayesha lost connection. Yes, ma'am, she has lost the connection. Okay, wait for 2 minutes, otherwise I'll call. Right.
Hello.
Yes, yes, ma'am. Yes, ma'am. Ayesha, camera is problem issue. You can.
I think I'll keep the camera off and
You keep camera off. Start.
right, because that is creating some problem. So I'm sharing my screen now. Thank you so much. Can you see my screen now?
Mm,
Okay.
yes, ma'am. Yes, we can see.
Yeah. Thank you so much. So I'm Dr. Ayesha Choudhary, as I've already been introduced so kindly. Thank you for inviting me for this presentation. And today I'm going to talk about distributed camera networks and their applications. This falls under the computer vision. So I'll give you a little idea about computer vision and single camera applications, and then move on to camera networks. So this is like the plan of the
Is
presentation.
it possible to switch over to this for slideshow mode?
I have switched over. Is it not visible?
What you can do is you can stop that window left side where we are seeing all the.
Okay, okay. Just a minute. I'll present again. I think I need to change the layout.
Mhm. Go to entire screen and then come.
Okay. Right. I think is my screen visible now? Is my screen visible?
Yes, visible.
Yes, ma'am.
Is it in slideshow? No.
Mhm. It is visible now and it is in full screen mode. No, earlier.
Ah,
Yeah, this is correct.
this is fine. Okay. Thank you so much. So sorry for all this confusion. So this is the plan. Let me start with the introduction. So why are cameras important? Like if you see as one of the most important sensors in today's world, and you see any application, you will have some amount of image or some video, and we are using images and videos every day in our communication, in trying to record something. So what is the camera that is really giving us? It is enabling us to see and record events that occur, and therefore we have a lot of information that we can then reuse to be able to, it could be just on the personal front, looking at your own memories, or in the professionally, you would want to, go back, and it could be like this lecture, you want to go back and see what is happening. So cameras are important, and now camera networks are becoming more and more popular because a camera has a limited view. We'll discuss this as we go. Now, in a camera network, what is important is that you cannot look at all the cameras. So if you see the security rooms in many buildings, they will have a huge array of displays where each display is showing, from a view from one camera, and it is not really possible for somebody to sit and watch all of this video continuously and keep a track of what is happening. So therefore, there's a need to automate and analyze the camera input. Also, if you want to go back and look at things, you would want to know what really happened in the whole scene at a particular time. And then also we need to basically automate, because it's not easy to go through every video and build the whole picture. But if we could analyze that data and then keep the data and use that information, it would be far more easier for us. So image acquisition, as we all know, there are various types of cameras that exist. And if you see this is a surveillance camera, which is just an RGB network camera. So a network camera is able to communicate. This is a Kinect, which has both an RGB camera, which is like a normal camera that images, as well as a depth sensor. So it is able to say how far something is from where the camera is placed. And this is a pan tilt zoom camera. So this camera can move its head, it can go up and down, and it can also zoom in and out. However, this is a static camera. It has fixed parameters. Now, what is computer vision? It is a subtopic of artificial intelligence which enables the computers to see. So when I say see, is when we see something, we are also able to derive information from it. So like our brain works along with the eyes to be able to analyze and say what is that we are looking at. Similarly, when we talk about a camera is only able to see. It is only able to image something. However, we need to have some algorithms on top of it which can tell us what exactly we are seeing and which can reconstruct the 3D world from images. So computer vision is the one that does that part. And when we do analytics, we sort of bring computer vision and machine learning together to be able to analyze what is being seen. And then we are able to come up with information that is useful to us. So very basically, I'll just go through this too, so that the rest of the presentation is sort of more understandable. This is what we have as a camera model, as a pinhole camera model, and it is the basis of all imaging. When we look at something, so you can think of this as your lens, your eye, or whatever is imaged. So the light falls on this particular point, and that light ray moves on to the image plane. So this is my camera lens, and this is my image plane, and an image is formed. And in general, when we have a camera model like this, the image formed is inverted. Even in our eyes, the same thing happens, and it is our brain that actually re-inverts this image. But for all practical purposes, what we imagine is that over here, if you see the image plane, this image plane is lying behind the lens, and that is why what we are getting is an inverted image. If the image plane was here in front of the camera lens, then what we would get would be a upright image. So mathematically, what we assume to be a pinhole camera model is that there is an image plane which is in front of the camera center, which is the pinhole over here. And there is a mathematics that we can easily develop based on this being a 3D point, this being an image of that 3D point which lies on the image plane, and this is the camera center. So we are saying that the image of this 3D point, capital X, is this small x. And now if you look at it over here, what this is forming is a triangle, and there are two triangles, right? So this is if we use similar triangles, then we can find a relationship between the 3D point, which is a capital X, and the 2D point, small x, in this form, where f is the focal length, right? So this is how the geometric relation between the 3D and 2D point is captured. This is a projection which is from R cube to R2. However, if we can see, this is a nonlinear function, and what we would like is a linear method to be able to, sort of simplify the mathematics and come up with what the exact 3D point was. Now, in this picture, what I would want to really explain is that what we see things is in the world coordinate system, right? We measure lengths, we measure you know, how long is my table, how high is my chair, and we do that within 3D coordinate system. When the camera is placed, the camera also has a coordinate system, right? And so there has to be a mapping between the world coordinate system as well as the camera coordinate system. Now we also have this image plane or the image. So when you click a picture, you have a picture. Any point in that picture, a picture is just a matrix of numbers, and any point in that picture has an XY position, right? So if I say this is the image of this cylinder, and over here this has a particular coordinate. Now the coordinate system of the image actually starts from this corner. However, if you want, you can also have a coordinate system over here. Now there are three coordinate systems. There's a world coordinate system, there is a camera coordinate system, and then there is a image coordinate system. To be able to go back from a point on this image and reconstruct the world, right? I want to reconstruct. So I have an image of the cylinder and I want to find out what was the height of the cylinder, right? And where was it placed in the world? Then I need to have a mapping between the image plane, the image coordinate system, as well as the world coordinate system. And this we do via the camera coordinate system. So the mapping between the camera coordinates and the image coordinates, as we just saw over here, this is the mapping that we are talking about. And how do we get this? So any point UV will be the X, which is now translated to this CXY. So the XY was a coordinate in this, over here is UV. So the XY was the coordinate in this plane where the 0, 0 is at this topmost corner. However, what we want is that should be in the center. So the principal point is also known as the principal point. So we add the principal point, which is just a translation. And this can be easily written in the matrix form, which gives us a linear method of writing, you know, the imaging function. So now we have the 2D point, we have the imaging matrix, and we have the point in the camera coordinate system. This is the 3D point in the camera coordinate system. However, as we can see, the camera coordinate system and the world coordinate system are related by the rotation and translation. And therefore, the complete projection matrix is a combination of K, which is this matrix, which is the matrix of internal parameters, and R and T, which relates my XYZ in the camera coordinate system with the XYZ in the world coordinate system, right? So this is how my projection is. So now given a world point and given this camera matrix, right, I know that my P of small x or my P of capital X is going to give me the small x. And therefore the small x can easily be, if I know capital X and small x, I should be able to find P. And if I know P and small x, I should be able to find capital X. And therefore we can reconstruct the world if we know the projection matrix. Now, why is this important? We will, as we move through the lecture, we will see that this is important because when you're trying to work in a network, right, you need to have calibration. And getting this P is known as getting that the calibration, you know, calibrating the camera. This is calibrating the internal parameters, and R and T is the rotation translation, which we can easily get when we are able to fix our world coordinate system in the view that we are looking at. So this is basically geometric computer vision. There are a lot of things that I use over here, but I'll not go more in depth. I just wanted to bring this so that, you know, the later part of the presentation is much easier and, you know, it makes more sense to you. So computer vision, as we know, this has lots and lots of applications. The applications are ever increasing. You know, it could be counting the number of people who are exiting or entering, crowd monitoring, you know, fall detection, assistive living, you know, just security surveillance, suspicious package, whether somebody is loitering, traffic monitoring, and lot of things. And lot of, so as I said earlier that, you know, you use machine learning along with the computer vision and you are able to get lot of information. So these are some of the single camera applications. So here we use only unsupervised learning. This was an experiment that we carried out using video from somewhere in the world. We have no idea of where this place is, and but just by analyzing the view of the camera, we were able to find out that it is very normal for people to walk across this road, and which seems normal also, that there's a road and people in any case will walk on it. And we came up with in different lighting conditions also we could find that something unusual also occurs in this area. And here it was a small cat that comes in. It comes in only in the evenings and night. During the day it was not sighted at all, because there are people who keep moving around in this area. And therefore, if you see, from just a single camera, we are able to capture certain information, use unsupervised learning. There's no training in this. It's just completely unsupervised, which is able to capture what is happening in the scene, what is usual and what is unusual. We moved on to a semi-supervised learning method, where you have certain amount of training data. So the system has certain amount of training data. We again do clustering over here, and we are able to then find out. So this is like a parking assist or a surveillance, where you just want to check whether the cars are being parked correctly or not. So if you see in this parking slot, it is very normal for cars to park in this manner, and the system was able to find out that yes, this car is getting parked in the correct manner. And however, although it has never seen this kind, it is then able to tell whether the car is being parked correctly or not. So it can assist the driver. It can, there can be an alert system that says no, or it can assist the person who's looking after the parking, that somebody is doing a wrong parking, something wrong is happening. And this is semi-supervised, where we have some label data only of the correct parking, but something that is not correct is flagged. Another single camera application that we are working on is fall detection, because fall is one of the accidents that leads to maximum health problems, especially in the elderly, and it is very important to be able to raise an alarm if somebody has fallen when they're alone. The difficulty in this case is that when a fall activity happens, so it is very similar to a normal activity happening. Now when this person is going down like this, it's just tying laces, right? Our system is able to say that this is a normal activity. But it could be that the person was trying to go down and tie laces, but instead of going down to tie laces, the person falls. And this should be raised as an alarm that the person has fallen. Similarly, a person trying and going to sit on a chair, it looks very normal and it should be flagged as a normal activity. However, it is not always normal. The person who's sitting on a chair can also fall down. So there's a lot of fine line between what is a normal activity and when a fall has occurred. And therefore, that is one of the biggest challenges in this work, is to find out correctly when a fall is happening, because an alarm system is continuously raising an alarm, so saying that there a fall has happened when a fall has not happened. People will sort of stop. So there are a lot of intelligent vehicle systems that are now prevalent and necessary. Lane detection is one of the important, safety systems that most developed cities have. And the important part over here, so this also, if you just look at this, and this is completely unsupervised. There is no supervision in the system, and it is able to, correctly find out even among these dashed lines where the lanes are. So especially in places where lane-based driving is done, if the vehicle tends to depart from the lane, it could lead to an accident, right? Because the driver in the other lane will not be aware that a vehicle from this lane will suddenly start departing. And therefore, if the vehicle starts to depart, we should be able to tell the driver that, the vehicle is moving away from the path that it should take. So that's a lane departure warning. And again, if you see over here, there are lanes are of different colors. This is a double lane, And the important part is this is a curved lane. So all that we have, we assume that there is a camera that is mounted over here in the front of the vehicle, and we are just able to assess where the lane is based on the view of the camera. This is on a two-wheeler. It's mounted on a motorcycle, again in a curved lane. So it is still able to, in an unsupervised manner, we have not taught the system anything. It learns on its own. So if you see, there are lots and lots of applications of single cameras that exist. However, there are a lot of limitations also. And one of the biggest limitations that a single camera application has is that the view of the camera is limited. So it works well. If you see, it works well in this case when you're trying to do a lane detection only in front. Now suppose we were moving in a very congested area, right? And I would want to know what is going to happen to the vehicles on the side of this road. Is a vehicle going to come and sort of bash into me, or what is happening behind me? Over here I can only work on something that is in front of me. So a single camera is then a limited a limitation. What we would need is to have a surrounding view. Similarly, if you look over here we have a very clean data. Very clean data. When the person is walking, you can see the whole person. There is absolutely no occlusion. Suppose this chair was in front of him, or suppose there was another table that was in front of him. We would not have the same view that we are having currently. And because we have no occlusion over here, we are able to still correctly define that the person has fallen. But what if he was occluded? We might not even be able to see what the activity was that was happening. So these are these limitations of occlusion, and then there's a limited view volume. You can only remain in the view of a camera for a certain time period, and once you are out of the view, we don't know what is happening outside of that view. So with a single camera, the surround information is not possible. So what we need camera networks. We need multiple cameras so that we can continuously view if the cameras are in the same room or the same area. Then you can continuously view from multiple views. If it is in a building, then you need a camera network to be able to cover the complete building, keep everybody in view. And therefore camera networks are very, very important and much needed in today's world. They help overcome the limitations of single camera. They help in the process of reconstruction. So reconstruction is the process that I just talked about initially when I talked about the pinhole camera, where you want to find out the camera matrix and then get back the information of the world from the images that we have. Now, what is a camera network? A camera network is a network that is formed by multiple cameras that can communicate among themselves. Right? We can have multiple cameras, but if they don't communicate, they don't really form a network as such. And they are dependent on the types of cameras that are used, the communication methods and storage, and how you do the computation and go about it. So types of cameras. We just saw that there are various types of cameras that exist. And I'm only talking about RGB cameras. There are also infrared cameras. There are just simple depth sensors only. But here I'm talking about, when I am talking about types of cameras, I'm saying RGB at least, right? And then beyond RGB. So the type of camera network depends on the type of cameras that you use in your network, right? So if you are using a static camera, only static cameras, which cannot pan till zoom, then we have what is known as a static camera network. You have to fix the view of each camera and then place the camera in such a manner that after the camera network has been placed, you cannot change what the camera is looking at. So we have to be, if you want to change the view, it has to, yes. Any message from you? I think somebody's mic is not muted.
Fatima John, please mute.
Yeah, thank you so much. Right. So when we have a static camera, may I continue?
Yes, ma'am. Yes, ma'am.
Thank you. So when we have a static camera network, we have cameras that are fixed, right? And that means that the views of the cameras are fixed. And if you want to change the view, it has to be done manually. In a dynamic or a PTZ camera network, the cameras can pan, tilt, and zoom, and therefore the view of the cameras are dynamic. They keep changing. So you cannot have a static background over here. Even the background can be something that is changing. You can also have a mixed camera network where you know that some cameras have to continuously look at something. So let those be static, and then there can be some dynamic cameras. And the camera networks, you can depend on the type of sensor that you are using. If it's an infrared camera, RGB camera, or depth sensor. So depending on those kinds of sensors that you're using, you can also have another type of a mixed multi-sensor camera network. Now, based on the type of communication, you can have a wired camera network depending on how big your room is, what type of a communication you require, or you can have wireless camera networks. And then you can have centralized computations where all the cameras are sending the information to one central server where all the computation and analysis is done. That's a centralized system. Or you can have a distributed camera network where every camera, so when I say camera, it's a smart camera. It has some processing, that is either you put a laptop or a desktop or a server along with that camera, or it is onboard camera processing. And so every camera does its own processing and then communicates with its neighbors. So in general, what we would really like is, maybe a wireless camera network which can communicate as well as it does distributed processing, and a mixed camera network where you can have cameras of different types. So here we then move from single to multiple camera, and we just talked about why we need those. So now I'm going to talk about a distributed method for self-calibration of a pan-tilt camera network. So I'll just introduce, we saw what was calibration, right? We saw that when we are calibrating a camera network, we will need to calibrate every camera in that network. That means we need that P matrix for every camera in this network. And this P matrix of every camera in the network should have the same world coordinate system. Because if I want to place a person in this complete camera network, suppose I say this person is over here, I should be able to give the world coordinates whether I am viewing it from all of these cameras in one coordinate system. So the important part over here is getting everybody in the same coordinate system. So that is what will give us the globally consistent and accurate parameters. We need all of these camera parameters to be in the same world coordinate system. Why do we want distributed processing? Because it should be robust to failure. I should be able to delete a camera, or I should be able to add more cameras to this network as per my requirement, so that I can increase the camera network or decrease the camera network. And then I need to ensure that there are no inconsistencies in the processing. So what we use over here is something that is known as multi-layered belief propagation. Belief propagation, I'm sure most people know that you just so everybody has a belief and they propagate this belief, and as the belief propagates, everybody sort of seems to have the same belief. When I say belief, I mean that the same parameter values. Right. And why do we call it multi-layered? Because we are going to do this propagation in different layers. The important thing to know over here is that because these cameras are pan tilt zoom cameras, they can pan tilt, and therefore their topology will keep on changing. Right. Over here we have a certain topology. If these cameras were static, this topology would be static also. But because these cameras can tilt and zoom, their topology will change. And when the topology changes, we will have different subgraphs or different subnetworks with within the same network. So these are challenges as well as this is what will give us good information. So very basically what we take care over here is that we assume that there's a communication network, right? That each camera has a unique ID and that the cameras will remain static for a certain time interval at least. So even if I'm changing the topology, after the change in the topology, the camera will stay in these positions for at least a certain time interval. And that the subnetwork consists of cameras that are viewing a common area. So every subnetwork will also form a complete graph. This is a subnetwork of this network, and this will form a complete graph because every camera in this subnetwork is able to communicate with every other camera in this subnetwork. So by itself, it is forming a complete graph. And because there are many subnetworks, if you look at this image again, although the topology has changed, only cameras that are looking at a common area are forming a subnetwork. They are complete by themselves and they are mutually exclusive, right? So there is no overlap between these subnetworks as long that we are taking into consideration. It could be that something that is viewing over here may be able to view something over here, but we are not going to consider that. We are only going to consider the area that all these three are viewing together. So to be able to calibrate, right, to be able to calibrate any camera network or a single camera, we need to have those small x, which are the image points. So every pixel in this image is actually that small x, which is the image of a 3D point. However, when we are doing calibration among multiple cameras, because we want it to be consistent, we want to use what is known as corresponding points. So I should be able to say that this point over here in image 1 corresponds to this point in image 2 and this point in image 3. And therefore these three image points are actually images of the same world point, and therefore they are corresponding points in images. Now we want a self-calibration method. When we say self-calibration, we want an automated calibration method. We don't want to use any specific calibration object to calibrate any of these cameras. So what we want is that, and when you talk about camera networks, see, camera networks also sort of bring in this notion of largeness of space. So you want to calibrate a camera network. Nobody has the ability to go and take a calibration object, put it in front of a camera, and then calibrate each camera separately. You want it to be calibrated as a system, and that has to be an automated system. So even I cannot sit down and really click points over here, and over here, and tell my system that these three are corresponding points. I mean, it can be done if you have just three cameras and looking at a certain object, which is this turns out to be a very nice object because you get lots of corners to be able to do. So what we used over here is shift features and pairwise shift matches. So you automatically find points that are scale invariant features, and you find then the matches between these points, and all the shift matches will what they're supposed to give you are corresponding points. And then we refine these shift matches by fitting fundamental matrices. So let me not go into the details, but this fundamental matrix is something that gives a relationship between two corresponding points. So if I said, if I said that this point corresponds to this point over here, then I am wrong, right? Because this is like the third cupboard and this is the fourth cupboard over here. So this point and this point will not be related by a fundamental matrix. However, if I have this point and this point, then there will be a matrix that will give me a relationship between these 2 points, and that matrix is called the fundamental matrix. Now, because we are talking about complete graphs means that, and we are talking about subnetworks, so they all have to look at the same scene. So these are 3 different cameras which are looking at the same scene. Now, if we knew the topology of the camera network, then we can reduce the number of computations for shift matches. Because suppose I had a fourth camera that was looking separately, which was not looking at any of these views, then I don't need to find whether a point over here corresponds to a point in that camera, right? So if I know the camera topology, or some idea of the camera topology, I know where all I have to look for corresponding points. So once we have the corresponding points, what we now want to do is calibrate each camera. So you can use a standard multi-camera self-calibration technique for calibrating the cameras within a graph. Because what happens is, there are methods to do calibration of a camera network, right? You have multiple camera calibration that happens. But the problem over here is the network is dynamic. It is a distributed system, and we want to calibrate every camera in the same coordinate system. So what we really need to do is, we really need to come up with a method where everything can be brought into one framework. So now, using a standard multi-camera calibration method, we can now calibrate the subgraphs, right? And why is it possible to calibrate the subgraphs? Because there are standard methods for this. And then what is the problem in, if I am able to calibrate this subgraph, and this subgraph, what is the problem that remains to be done? The problem that remains to be done is that if I have calibrated each subgraph, I have still not calibrated the relationship that will bring all of this under one roof, bringing them all into the same world coordinate system. So we show that it is possible to calibrate the complete graph, not each subgraph, by calibrating 3 clicks. So a click is a small complete subgraph. And if we have a click of size 3, that means if we take 3 cameras that are in one subgraph and use multi-layered belief propagation, then we can calibrate the whole network. So the estimates of the camera parameter for all cameras in a click, right, which is computed using multi-camera self-calibration, are considered as the belief of that node. And then we use these belief update equations to be able to compute the sigma ik's and the mu ik's, which are the estimates of the ith camera in the gkth click. So this is something, I think this might be easier to understand. So this is one click, right? And this one click has 3 cameras, C1, C3 and C4. Now this does a multi-camera calibration, and it comes up with an estimate for P1, P3 and P4. This also does a multi-camera calibration and comes up with an estimate for P1, P3, P4. So the P's are the camera matrices. And this also does the same computations to come up with an estimate. Now, because of a lot of errors in the rounding of errors in computations of pseudo inverses, doing SVD, to be able to come up with these parameters, P11, P13 and P14 will not be the same, right? There will be some sort of a difference in each one of them. So what happens? C1, C3, C4 communicate their camera matrices with each of these in the click, and belief propagation occurs, and what we come up with is a P1 that is consistent in graph 1, a P3 and a P4, and all these are consistent in this graph. Now if you look at it, this was a click. C1, C2, C3, C4, C5 was also a click, but here we are doing only computation between 3. Why? Because this is sufficient to be able to calibrate a bigger network. Now, once we do C1, C2, once we do C1, C3, C4, we can similarly do C1, C5, C2 also. And over here also, we will come up with an estimate for each of the camera matrices at each of these nodes. Having done this, what we have is, we have a measure of P1, which is in graph 2, and we have a measure of P1, which we get from graph 1. Over here also, we do belief propagation. Now we need to come up with a consistent estimate, right? And if we keep doing this among the different clicks, after a certain point in time, we will have one consistent P1 that every camera will know. So over here again we do a belief propagation to come up with a consistent P1 between G1 and G2, between this graph and this graph. And if we repeat this for every click, we will have what is known as one camera matrix for C1, one for C2, one for C3, one for C4, and one for C5. So this is what we are doing in one click. Now the same thing can be repeated among different clicks. So if I don't know whether I have this here. So over here, this works even if you have a static camera network, right? Because every camera over here is static. And by using the camera calibration within clicks, we are able to self-calibrate a static camera network. And if you look at it, I don't know if you can see it in the images, but this is for 5 cameras. And after multi-layered belief propagation at each node, we are able to get the error in reprojection, which if you look at, if we were just taking a random set, so suppose like over here, we are considering only the P1 value in graph 1 and doing reconstruction, and the mean error is 8.67. Similarly, here we are taking the P1 from graph 3 and doing reconstruction or reprojection error, the mean is 13.41. So that means that there is a difference of at least 13 pixels between the original point and the point that we have reconstructed. But over here, after multi-layered belief propagation, the error goes down. The mean error becomes 1.8, and so does the standard deviation go down. Where over here, if you see the standard deviation, and this is for different cameras that we have been able to show. Now, if you look at it, depending on the view, right, the orientation of the camera, the errors still don't go down. If the view is sort of more clear, the errors are less. If the view is oblique or it's very small, here it is very difficult to define the pixel, the exact corresponding point also. So the error will be very high. But despite that, if you look over here, the error was 10.97 over here, and by after multi-layered belief propagation, it goes down to 2 pixels. So this was self-calibrating the static camera network. But now what happens? This is a click in the static camera network, which we have been able to calibrate. And so we have values of camera matrix for each one of these cameras. We pick up camera C2, which has the camera matrix P2 in this GK. Now, GK is this graph. Now, if you look at the Pantel camera network, what has happened? If this camera pans and or tilts, and if this camera also pans and tilts, and this camera also pans and tilts, we get a new subnetwork. Right? So there is this network breaks. There is a subnetwork now by this camera these 3 cameras. There is a subnetwork formed by these 3 cameras, and certain subnetworks are formed. Now, what do you do in this case? The camera matrix now, since the camera is looking at something else, if I just do a calibration in this static camera network, that camera matrix will not be the same as this camera matrix. So although I'm talking about C2 over here, the parameters that I am getting will change because the orientation of the camera has changed. So here we need to bring it to one home position, right? We have a camera because it was looking in this direction. It has a camera matrix here because of that RNT that exists, that initially that I had told, that corresponding to the world coordinate system, there's a camera coordinate system which are related by a rotation and translation. Now here, if you look at it, this has rotated, right? This camera has rotated. So once the RNT have changed, so P will change because P is equal to K into RNT. So K will not change, but the RNT will change. So what do we need to do? I now need to bring this to the home position, and I now need to bring this also to the home position because that is a position at which I can compare these two, right? And that home position is where there is 0 pan and 0 tilt, which we know that 2 camera views are related by a homography. Homography is again a linear transformation, and I can go from this view to my home position using the homography matrix that can be easily computed. And similarly from this view to the home view, again by computing another homography matrix. Once I have two camera matrices for the same view, I can now again use belief propagation and update my equations to come up with one camera matrix. Now, if we keep repeating this procedure, right, we can keep repeating and we can, this is the why I call it multi-layered belief propagation, because we are now propagating belief between different layers. And here we are now then finally the update equations will become consistent and we will get this camera matrix for every camera in the network with respect to the same world coordinate system. Right. Here the update equations are now dependent on the update at the parameters at I home for k minus 1 and parameters at I home at k. Now, to be able to do that, right, to be able to do my multi-layered belief propagation, I need that the network should change after certain time period. Because if the network does not change, then this is as good as a static camera network and I am not able to change between the fan and tilt. So we need to form new graphs, and therefore here what we do is we make the cameras look at new landmarks in the system so that the camera network keeps changing. And once the new graphs are formed, we repeat this procedure to be able to calibrate the complete system. Since this is a self-calibration method, if it's an outdoor camera network because of wind, because of rain, because of certain, somebody is touched or something else is touched, if the camera view changes, we can recalibrate the system very easily. And even in an indoor camera system, there are times, you need to do something, you need to move the camera. If that has also happened, it can be easily recalibrated. It is very difficult to see probably, but over here, if you look at these, I don't know if it is visible, but you can see some red circles and green marks, right? So the green marks are the original points and the red circles are the reprojected points, and it can be seen very easily that the reprojection error is very low. Where we have actually marked the initial point, we have also got the reprojection. So belief propagation within a graph, it leads to consistent estimates of the camera parameters, and then as we move on, we see that the reprojections after distributed calibration. So this is reprojection after distributed calibration. If you see all these yellow points and the red point, they are sort of falling together. And I am randomly choosing the camera where I am doing the reprojection, but I am able to get in both the cases that here if you randomly choose and do reprojection without doing belief propagation, the red points are different and the yellow points are different. But here if you look at this was done after belief propagation and the reprojection falls where the original points are. So it can be seen that when you do belief propagation, you are able to get a good reprojection. That means your camera matrices are correct. Over here, if I just randomly choose camera 1 from one of the graphs, then what I'm getting 20 as my mean error in reprojection. But when I do belief propagation, all my cameras in every graph, right, have the same camera matrix which is consistent and the error is less than 1 pixel. So this is how belief propagation can be used to update parameters and get a consistent calibration for the sensor. Again, this is reprojection at home position of C1 after multi-layered belief propagation from 7 graphs. So 7 parallel graphs, and this is reprojection after belief propagation containing C1 at the home position. And you can see that when you do belief propagation only within a graph, the error is still 3.13, but after belief propagation across multiple graphs, the error goes down to less than 1 pixel, and therefore the reprojection is much better. Similarly, over here, this is reprojection on home position of all 6 cameras in our network. And as can be seen, the mean error is less than 1 pixel in every camera. This is after belief propagation across the Pantel network. Okay, so now the question that arises is, why are we even trying to do this, right? Why are we even trying to calibrate the camera? Now, the important question over here, the important answer over here is, obviously you can calibrate because it is important to calibrate. But now suppose that, so if instead of this computer there was a person standing over here and moving around in this area, I would, and if I want to trace and tell what is the 3D position of that person with respect to, let's say, a world coordinate system that is lying over here, right? I can say how far that person is over here. And when the person moves in this area, I should be able to tell where the person is going in the camera network. If two cameras are looking at the same person, and if I know the correct 3D position, both the cameras can say that it is the same person, because at a particular 3D position, there can only be one person at a time. That's something that is, I mean, physically it is not possible for two people to stand at the same spot at the same time. So if these two cameras are saying that there is a particular thing at the 3D position, then I know it is the same thing in the two scenes. So therefore, I need to calibrate a camera's network to be able to come up with one consistent story. So we use this calibrated Pantel camera network for a distributed framework for composite event recognition. When I say a composite event recognition, I mean that events that occur simultaneously or sequentially across space and time. So it could be that within one camera network, I'm simultaneously watching what the event is, and across the camera network, across time, I'm able to say that, okay, within this subnetwork, I saw this person, now this person has moved out of that subnetwork and gone into another subnetwork. Do I have time? So there are two problems that need to be addressed. How much time do I have?
Well, you can take the session till 5 o'clock.
Okay, but there's some discussion time.
Yes.
Right? Okay. So I think this is not the last portion. I'll just quickly go through this. So the two sub-problems that need to be addressed over here is that we need to do tracking within the camera subnetworks as well as across subnetworks. And then we need to recognize what is the complete event that has happened. And the event that we look at over here are pairwise interaction. When I say pairwise, it's interaction between two objects. So these are the things that we really need to do. We need to detect the objects. We need to track objects across space and time. We need to recognize, what is the event. And using the sequence of the event to recognize the composite, we need to have information from each subnetwork. And we need to fuse that information, as well as we need to fuse information across subnetworks to come up with the complete story. Now, to be able to do this, we have to have certain assumptions. So we assume that the Pantel camera network is calibrated, which is very important. We assume that communication exists, and because the cameras need to talk to each other, that for a time period, all cameras will have sufficient overlap, and that is how they can form a graph. And that the cameras pan and tilt in discrete steps. So it will remain in one position for a certain time period. After it pans and tilts, it changes its position and then stays in that position for a certain time period. So it is not something that keeps moving across, keeps sort of panning and tilting. It pans and tilts and stays in the next position for some time. And when it does that, it needs to now know which cameras are there in its subnetwork. So once it pans and tilts, it sends a message to all its neighbors about its new Pantel position. And then it also needs to find out that which is the click or which is the complete subgraph that it is forming. So this is sort of the event architecture that we have, that for each camera will capture the image, find the graph that it belongs to. It does things like object detection, tracking, and event recognition. And this is then over time, when you have every camera, it does this, every camera does this, goes through this pipeline. And then it comes on a consensus on the global identity of the person, as well as, or the object, as well as the consensus on the event that it has recognized. It could be as simple as that, yes, this person has worked on this path. And then from each of these subgraphs, we have different subgraphs because the cameras keep panning and tilting. We need to then bring all of this information, and we use the hidden Markov model for composite event recognition. Okay, let me not go too much into technical details, but since the camera remains static for a certain time period, we use background subtraction to detect the object, and then we have a calibrated camera so we can find the 3D position and track the object based on many features of the object that is seen, detected. Right? And then we check the message received from neighbors about the object to give it a global identity, right? Which is a probability, as you can see over here. And based on, whether you have a prior probability from a previous graph, you give it a certain probability. If the person is new, which has not been seen, you give it a certain probability. And then the most probable hypothesis is what is taken as the map estimate of the belief of the graph about the object's identity. Now, events are considered as pairwise interactions. Now, how do we know what is a pairwise interaction? So we apply probabilistic latent semantic analysis to learn the pre-specified number of pairwise interactions. So here is where supervised learning comes in. We are learning what are the interactions that can happen. And consensus on the interaction using belief propagation within a graph. This is necessary because each camera will compute PLSA probabilities based on the features that it has seen. And therefore, there is an associated uncertainty with it. So then, using these PLSA probabilities, we come up with a map estimate, which we say is the belief of the system. And then we use hidden Markov model using these PLSA probabilities to be able to come up with the complete event that has happened. So let me just show this result. So this is a camera network of 3 cameras. These 2 are pan-tilt cameras. This is a static camera. And the videos are not synchronized, so you may see something happening over here, something happening over here. But these 2 are looking at the same area, right? So they are also forming a subgraph. Now, as this person walks, you can see that both these cameras are giving it a red track. That is like, defining the identity of the person. So since they're not synchronized, this one move, you feel as if this person is moving faster, and this is actually able to see only a part of the scene that is happening over here. And this is a completely separate camera. So as you see, this camera has panned. Similarly, let me switch this on. This also pans, and then this person removes this bag and moves away. While there's another person in the scene who is now entering in this area. Actually, this should be a little faster. And if you see this, let me stop. This is a little confusing. So this person had a green track. This person continues to have a green track, and in this camera network also. So that means that the camera network has reached a consensus on the identity of these 2 people, because this was red over here, this person is red over here, and this was green over here, this person is green, and there's a blue track for this bag, and it is a static object once it has been put down. So nothing happens. This person just moves. The story basically is that this person comes, leaves the bag, but this person does not, sort of tamper with the bag and just moves away. And the identities are maintained because the color of the track shows. Also, when this camera panned, the red continued. So that means that after panning also, the person was correctly tracked. So the global identity remained. Now this is the same thing, but here we have an unusual event. So there is this person who comes. Let me make him move a little faster. This is very slow. So if you see this track, you can also tell a lot about, how the person is working. And while this person is in that scene, this person again comes with an object in their hand. As in the previous case, this person leaves the object over here, and as she's about to go as she's about to leave the scene, this camera has panned to continue tracking. She leaves this object and she moves out. And similarly over here, she leaves the object and she moves out. The global consistency is happening, and as she enters the scene, he's still over here. There's nothing that is happening to the object in the scene. Now she moves into this area and she'll just go out while this person has also gone out of the scene. So for some time period, there is nobody in the scene. This person has gone out, this person has also gone out. Let me just put a pause on this. Now we see that this person has come back into the scene, and what he has done is the interaction over here is now different. Right? This has got recognized as an unusual event because the interaction in the previous thing was usual, that somebody comes and leaves and nothing happens. But the interaction in this case is unusual because this was an event that was not seen earlier. And the cameras again pan and tilt back to the same position to continue tracking this person in the scene as long as it can be tracked. So this complete story is being recognized as an unusual event from the HMM part. The interactions are being recognized by the PLSA part. And this all is possible, the global identities are maintained because of the calibrated network. And here, as you see that as the cameras pan and tilt, they are still able to communicate among themselves and say that it's the same person that they were viewing in the earlier pan tilt position. So I would like to now conclude. As we saw that camera networks have a wide variety of actually camera themselves have a wide variety of applications. However, camera networks have even wider variety, and various machine learning algorithms can be applied along with the image and video data. So we had unsupervised learning, we had semi-supervised learning, we have a mix of we have completely supervised learning, like in this case we had PLSA and HMM, which need to be, and then now in recent cases, if you see the, I think that I did not show over here, but now we are also working on deep learning along with the vision data to come up with more accurate solutions. Camera calibration is important. It is a very important thing because whenever you're talking about a camera network, you need to talk about everything in the same coordinate system. So I think I'll just end over here and open it for discussion. Any questions? May I stop presenting?
Yes. Yes.
Okay, so I go back to my screen. Can you see me?
Participants, you can ask questions.
Okay, so any questions? Any points? I mean, not just questions. You can, any comments?
Ma'am, is there any particular software for doing research in this area?
No particular software as such, but you could use any programming language. There is an OpenCV library that helps you in implementing the image processing and vision part. But
Okay.
otherwise, you can implement this in C, C++, Python, Java, whatever you're comfortable.
Okay, ma'am. Thank you.
Ma'am, can we take some data point and apply this in machine learning or especially in reinforcement learning algorithm?
What do you mean by data point?
Means, ma'am, some data which is related to some pics or some pictures,
Yes,
and apply the reinforcement learning on that point.
yes. Reinforcement learning is a very important learning algorithm that is used with vision data to train systems.
Thank you, ma'am.
Okay.
Okay. So should we conclude the session, ma'am? Okay, Kanksha, please conclude the session.
Thank you, ma'am. We would like to thank Ayesha, ma'am, who honored this FDP and enlightening all of us with her expertise. Thank you so much, ma'am, for this informative lecture. We learned various important aspects: pinhole camera model, camera coordinate system, camera networks, intelligent systems, and many more. Ma'am, these are the main topic of research in present scenario. So, ma'am, it was very informative lecture. Thank you so much, ma'am.
Thank you so much, Akansha, and thank you so much, Professor Kaur.